All right, welcome everybody. Today we're going to talk about lesson number 60, and this is the second day of solving trig equations in section 5.3. The truth is your goal is still the same as it was in lesson 59. You're trying to isolate the trig functions, then you're trying to solve using the unit circle. Sometimes you're being asked to find the general solution, and sometimes you're only being asked to find from 0 to 2 pi. Here in the second day, we're going to have more substitutions using the formula sheet. We're going to have some fancier solution techniques, and then we're going to see a couple of examples where we have to check for extraneous solutions. But really, today's lesson just kind of reinforces lesson 59 and is an excellent review. So let's take a look here at number 1. Find all the solutions from 0 to 2 pi. Remember, it will never be a secret what interval you're supposed to be solving in. You just have to be mindful of it. So the first thing you want to notice here is that everybody is a sine. If everybody is the same trig function, that generally means the problem is going to be a little bit simpler than if you have more than one trig function. The second thing you hopefully notice is that this is, again, another example of quadratic form, a problem that looks like a quadratic, meaning you can solve it the same way, but instead of doing it with just x's, you're going to do it in this case with sines of x's. So in order to solve this, we do want to be equal to 0, which we are. And I'm going to go ahead and show you this using the AC method, which is factoring. I'm going to show you one in a minute where we're going to do the quadratic formula. And remember, if you don't have to do the entire AC method and you can kind of just guess and check or jump right to the factoring, that's fine too. Do as many or as few steps as are needed. But let's say you are going to do the AC method, just like whether you have sines or just x's, you're going to multiply 2 times 1. That's going to give you positive 2. You would then have to find 2 factors of positive 2 that added up to be negative 3. And that's going to be negative 2 and negative 1. You're going to go ahead and use those values to split up this middle term. And just make sure when you do so that you do it in terms of sines. So this is ultimately going to be 2 sine squared minus 2 sine x minus 1 sine x plus 1 equals 0. Hopefully you remember that grouping is the next step. So take the GCF out of the first pair, which would be 2 sine. That's going to leave you with a sine x minus 1. Then you're going to take the GCF out of the second pair. And again, when in doubt, take the negative out. So I'm going to take out a negative 1, which is going to leave me with a sine of x minus 1. Hopefully, again, from the good old days, you remember that when you get that repeat factor, that's a really good sign because that means that you're doing it correctly. Whatever that repeat factor is going to be half your answer. And whatever is on the outside is going to be your other answer. So sine of x minus 1 times 2 sine x minus 1 equals 0. You're going to go ahead now and set each of these parentheses equal to 0, which means that sine of x is either equal to 1 or the sine of x is equal to positive 1/2. Keep in mind that you are solving here. It's just one revolution around the circle. So if you're talking about where the sine is equal to 1, the sine is, of course, a y value, and that would happen up here at 90 degrees, which of course you're going to tell me is pi over 2. Remember, you don't have to draw the picture. You can pull up the unit circle. The easier you're able to do it without referring to something, it's just more efficient and it just helps you to remember. For the sine equaling positive 1/2, again, sines are y values, which are positive in quadrants 1 and 2. So I know that I'm going to have answers in quadrants 1 and 2. Then you just have to make sure that you have the right family. The family that has a sine of 1/2 would be pi over 6. So it's pi over 6 in quadrant 1, and then 5 pi over 6 in quadrant 2. Now, again, I've been doing this for so long that I happen to know these values off the top of my head. I don't have to look them up. But remember, until you get 100% confident in your ability to do that, you should refer to your formula sheet and your unit circle as necessary. So here there are exactly 3 answers. Remember, there's no way of knowing ahead of time how many answers there are going to be. So you have to be prepared for all contingencies. Here in number 2, now we're going to be finding the general solution. So again, that means there's infinitely many answers, and you're going to have to decide where's the starting point, and should it be pi n or 2 pi n or pi over 2n. And here, the first thing that hopefully jumps out at you is that you actually don't have just one trig function, but you actually have 2 trig functions. You have a sine and you have a cosine. So you would like it to be all just one single function. So you're going to go ahead and use your formula sheet to make a substitution. The only thing that I could possibly substitute for cosine would be 1 over secant. That does not help me in the slightest, which is why sine squared is where the action is going to be. So here for the sine squared, that's what I'm going to go ahead and replace. And then if you look at your formula sheet, sine squared is, of course, equal to 1 minus cosine squared. We've probably made that particular substitution at least 50 times over the last couple weeks. So hopefully it's getting simpler to do so. So from here, I'm going to go ahead and distribute. So 2 minus 2 cosine squared plus 3 cos x minus 3 equals 0. I'm going to combine my like terms and put it in standard form. So negative 2 cosine squared plus 3 cosine of x minus 1 equals 0. While this is a fine format to solve the answer in, it would be just a little bit nicer if instead of having a negative 2 squared, I had a positive. So I'm just going to go ahead and divide everything by a negative. That's going to give me a positive 2 cosine squared, a negative 3 cosine of x, and a positive 1. Again, that just happens to be my personal preference, and one that I would actually strongly recommend is having a positive leading term. Just tends to be a little bit simpler for the solution process, but if you can do it either way, then by all means. This is again an example of a problem where if you were going to factor it, you would have to use the AC method. Since we already saw one like that, we're going to go ahead and use the quadratic formula. You're going to use the quadratic formula the same way that you always do, except instead of being x equals, in this case, it's going to be cos of x equals. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So the cosine of x equals 3 plus or minus. Under the radical, you get 9 minus 8, which of course would be 1. So 3 plus or minus 1 over 4. That's going to give you that the cosine of x equals, so 3 plus 1 is 4, divided by 4 is 1. Or 3 minus 1 is 2, divided by 4 is a half. So you're simply going to go ahead and divide it up into the two pieces. Then you're going to go ahead and give me the answers for each one. So starting with the cosine of x is equal to 1. If you think about the unit circle, the only place that has a cosine value of positive 1 is here at 0. Remember, you then have to go all the way around in order to get all the answers. So 0, 2 pi, 4 pi. The easiest way to say that is 2 pi n. That means any multiple of 2 pi, which includes 0. Then the cosine equaling positive 1/2. Well, cosines are x values, so you're going to need quadrant 1, and you're going to need quadrant 4. Then you have to make sure you have the correct family. So the family would be the pi over 3 family, and it would be 5 pi over 3 in quadrant 4. Again, notice how those two values are not spaced equally apart. That's how you know you have to write an answer interval for each one, as opposed to just one that connects them both. So your first one is going to be starting at pi over 3 and then all the way around, so plus 2 pi n. And your final is going to be 5 pi over 3 plus 2 pi n. So again, technically there are infinitely many answers, and in order to find all of those answers, you have to make sure that you write each of those three intervals. Oh, class notebook, a little bit glitchy. Hang on just one second. Okay, so x equals okay, think we got it now. X equals 2 pi n, and then pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. So you do have to have all of these equations in order to get all of the solutions. All right, so here in number 3, we're going to be trying a different technique, but we're again going to be doing the general solution. So again, each of your answers is going to be an equation. What you notice here is that you, again, do not have the same variable, but in this case, you don't have anybody that's squared, and you do have the sine and the cosecant, which do have a relationship. So the first thing I'm going to do is I'm going to go ahead and rewrite that cosecant as 1 over sine. And I'm also going to subtract 1 in the same step, just to get everybody on the same side. And then I don't like that some of these guys have fractions and some of them don't. So I want to get rid of this sign on the bottom. There's a couple of different ways that I could do that. The easiest way, though, is to multiply each of the terms in this equation. Hang on, it's just lagging a little bit again here. Okay. So again, I want to get rid of this sign in the bottom. And the easiest way for me to do that is I'm going to multiply everything in this equation by a sine of x. So just make sure that you do it carefully. When you multiply sine of x times 2 sine of x, that's going to give you 2 sine squared of x. When you multiply sine of x by negative 1 over sine, the signs are going to cancel, and you're just going to get a negative 1. When you multiply sine of x times negative 1, you're going to get a negative sign. And when you multiply sine of x times 0, the right side is going to remain a 0. This looks pretty good, except I'm just going to rewrite it in the order that I am used to. From here, you could, again, use the quadratic formula, or you could use the AC method, or again, maybe you're a stud out there who just can factor this by guessing and checking. The fact that there's a 2 sine, you know that it has to be a 2 sine and a sine. The only things that could possibly multiply to be 1 or 1 and 1, then you just have to find the correct positivity and negativity, and it turns out that this is the one that's going to work. So again, whatever you have to do to get the answers, you can use the quadratic formula, you can factor it, you can guess and check it. However you're used to factoring, you should continue to do that here. If you set each of these parentheses equal to 0, you're going to get on the left that the sine of x equals negative a half, where on the right, the sine of x is equal to 1. Just to again point out here, not every value for the rest of the chapter is going to be on the unit circle, but they are going to be there still for today and for tonight. We'll be bringing in those non-unit circle values soon, but for now, we're going to stick with just the unit circle. So I'll actually do the easier one first. So where is the sine equal to 1? Remember, sines are y values, so that's up here at pi over 2. Since that's the only one, you'd have to go all the way around to get back. So one of my answer sets is pi over 2 plus 2 pi n. Remember 2n pi, they're the same thing. In order to get a negative sign, which is of course a negative y value, I'm going to have to be in quadrants 3 and 4. So in quadrants 3 and 4, you then have to make sure you have the right family. So this is the pi over 6 family, and so it's 7 and 11 pi over 6 in those respective quadrants. And again, if you notice that those two answers are not equally spaced, that's how you know that each of those is going to get their own 2 pi n. The only way you're able to write it in a more efficient manner is if there is equidistance between each of those answers. So I'm going to go ahead and need an equation for each. Again, there are infinitely many answers in this case, so you're going to have to go ahead and find each one. So again, nothing really new for those. Yes, you had to make more substitutions than the past. And yes, you had to do some fancier algebra techniques, but again, nothing really brand new. For these last two, there is a technique that you just haven't done ever for trig functions. So we're going to go ahead and make sure we give a little bit of extra care to those. So here for number 4, we're again going to be finding the general solution. And we have the sine of x plus the cosine of x equaling 0. From here, what we want to notice is we have two different trig functions, and neither of them are squared. So I don't have any squared so far. I could rewrite the sine as 1 over cosecant. I could rewrite the cosine as 1 over secant. Neither of those is going to help me. If you're thinking to yourself, okay, well, I want some square terms, so I'm going to square both sides. That actually is the method we want to do, but not yet. If you were to square both sides in this step, you would have to do a FOIL on the left. That would leave you with a 2 sine cos, which right now is not something that we're able to solve. So we are actually going to not FOIL, at least not in the first step. Before we FOIL, we're going to go ahead and subtract the cosine to the right-hand side so that I have the sine of x equals the negative cosine of x. And then when I square from here, that's going to make it a much easier endeavor. So again, from here, I am now going to square both sides. And I'm just going to go ahead and write myself a little note here. So we are going to square both sides. When you square both sides, though, you have to be careful. When you do that, you are possibly creating extraneous solutions. You've heard that word many a time in your mathematical career, although again, maybe not lately. So if you square both sides, you're going to get possible extraneous solutions, which means answers that don't actually work when you plug them into check. And again, why are you looking for this? It's because you're squaring both sides. We haven't yet had to check anything because this is the first time we've squared both sides. So if I square the left side, I'm going to get a positive sine squared. If I square the right side, I'm going to get a positive cosine squared. That's much better because now that I have those squares, I can now use my Pythagorean identities. And really, it's up to you. Do you want to make it all sines or do you want to make it all cosines? I promise it won't matter. I'm going to go the sine route. So sine squared equals 1 minus sine squared. I'm going to then put all the sine squares on the left side, in which case there'll be 2 of them. Then I'm going to add my, or leave the 1 and then divide by 2. To get rid of a squared, you are going to take the square root. When you take a square root, don't ever forget your plus or minus. And then the square root of 1 over the square root of 2. If you go ahead and rationalize that, you're going to get plus or minus root 2 over 2. So notice that it implies that it's all 4 quadrants because of the fact that it's a plus or minus. So the plus or minus, sorry, class notebook, again, is just a little slow on the uptake. So plus or minus implies all 4 quadrants. And then additionally, the root 2 over 2, if you look at your unit circle and you're looking for the family that has y values of root 2 over 2, it's the pi over 4 family. But again, because we squared both sides, we have to check to see if all 4 of those solutions actually work. How do we actually check it? Well, we have to check in the original. Sorry, I'd restart it, but we're almost done here. So you have to check in the original equation. So again, think about what this is implying here. This is implying that it's all 4 families in all 4 quadrants. If you go back to the original problem was the sine of x plus the cosine of x is equal to 0. In order for that to be the case, the sine of x plus the cosine of x equaling 0. So I'll write myself over here. If sine of x plus cos of x equals 0, then sine of x has to be equal to negative cosine of x. The only way that they can add together to give you 0 is if they're exact opposites. So think about the 4 quadrants. In order for them to be exact opposites, one of them has to be positive and one of them has to be negative. So of the 4 quadrants, which of the 4 quadrants has 1 positive value and 1 negative value? Well, that would be in quadrant 2 and in quadrant 4. So those are the only places that I'm going to find my solutions. Again, quadrant 2 and quadrant 4. And again, it's because when I go to check them, the only possible way that those 2 things can cancel out is if one is positive and one is negative. So that means that for my final answer, after I do all that checking, my final answer is only going to be the answers in quadrants 2 and 4. So this is the pi over 4 family, which means this here is 3 pi over 4. This is 7 pi over 4. But notice that because it's the pi over 4 family, it's equidistant from 3 pi over 4 to 7 pi over 4. So I'm going to be able to find all the answers if I say 3 pi over 4 plus pi n. So let me just kind of zoom out for a second just to kind of rehash that whole thing from start to finish. Again, because of the fact that I had a single sine and a single cosine, that's why I had to eventually square both sides. When you square both sides, that is what is potentially creating those extraneous solutions. After I square both sides, make the substitution, take the square root, the plus or minus implies it's all four quadrants and all four values of the pi over 4 family. When I do the check step, which again you have to do in the original, the only way that the sine plus the cosine can cancel out altogether is if the sine and the cosines are opposite signs, meaning opposite pluses and minuses. That only happens in quadrants 2 and 4, so I can write the answers as one equation, 3 pi over 4 plus pi n or n pi, dealer's choice. One last example, again, find all the solutions from 0 to 2 pi. So you just have to be mindful of the interval that's being asked. So 0 to 2 pi it is. Take a look here again. We've got some trouble. We've got two different functions. Nobody is squared. There are no good options other than for me to square both sides. So squaring both sides, please make sure you're aware it is the last resort. You should try literally anything else first. There was no rewriting, no rearranging of the terms that was going to be more helpful. So in this case, on the left, I'm going to go ahead and make sure that I do the FOIL. Common mistake is people don't. So cosine times cosine is cosine squared, and then 2 cosine for the outers and inners, plus 1 equals sine squared. In the previous problem, it was up to you whether you went sines or cosines. In this problem, you really only have one choice. Because of the fact that you have this regular cosine, that means you have to turn everything into a cosine. So cosine squared, sorry, just one second. So cosine squared plus 2 cosine plus 1 equals 1 minus cosine squared. Notice that the ones are going to cancel, and then I'm going to move this cosine squared to the other side. So that's going to give me 2 cosine squared plus 2 cosine equals 0. I'm going to factor out the greatest common factor from each of these terms, which would be a 2 cosine. That is going to leave me with a cosine of x plus 1 equals 0. Set each of these quantities equal to 0, and you're either going to get that the cosine of x is 0 or the cosine of x is negative 1. If you think about where the cosine is equal to 0, remember those are the x values. So those are going to give you, I'll say, potential answers of pi over 2 and 3 pi over 2. Remember potential because we have to check them. And then the cosine equals negative 1 only over here at pi. So these are the 3 potential answers. Again, you now have to check them in the original. And while you can use your calculator, you have to be in radian mode, of course. But to be honest, for something simple like this, it generally is easier to just use the equation and then the unit circle as needed. So again, the equation that we started with was the cosine of x plus 1 is equal to the sine of x. So cosine of x plus 1 is equal to the sine of x. So we're going to check each of those 3 possibilities by plugging those in. So if I'm checking pi over 2, I have to find the cosine of pi over 2. The cosine of pi over 2 is 0 plus 1. Does that equal the sine of pi over 2? And the sine of pi over 2 is 1. 0 plus 1 equals 1. Yes, it does. Again, if you're wondering, where did I get those zeros and ones from? I got them from the unit circle. I would go up to my pi over 2. I would look at the ordered pair. If I'm talking about the cosines, I would look at the x's. If I'm talking about the sines, I would look at the y's. If you still find yourself unable to calculate unit circle values, please reach out as soon as possible because that's going to haunt you all chapter long. So now for 3 pi over 2, the cosine of 3 pi over 2 is in fact 0 plus 1. Does that equal the sine of 3 pi over 2? And the sine of 3 pi over 2 is actually -1. So that's a lie, which means 3 pi over 2 has to be rejected. And then finally for pi, the cosine of pi is -1 plus 1. The sine of pi is 0. So we have another winner, which means the only two possible answers to this equation are pi over 2 and pi. So again, the first three problems, just kind of general reminders of how you solve, bringing back some of those factoring and quadratic formula. Here in the final two, you had to square both sides, which means you have to check your solution. And then to finish up, I just wanted to, again, bring back a few additional reminders for you to keep in mind as you solve. As a quick reminder, here are examples of problems that have no solution. If you were to get the sine of x equal to 4, remember that there would be no answer to that because 4 is too big. Your sine and cosine range is only -1 to 1. Another example of an equation which would be no solution would be sine squared equals -1. Think about why that is. If you take the square root of a negative, that's imaginary. We're not going to do that. Then something else, this is really more for the next lesson, but it doesn't hurt to kind of just remind it here. Let's say that I asked you to multiply the tangent of x times the tangent of x. You can do that and rewrite it as the tangent squared of x. What we're going to see next time is instead of having just a single x, maybe we'll have something like a 2x. When it comes to multiplying, if these are the same, you can multiply that to be tangent squared of 2x. The only thing you can't do is what if you try to multiply the tangent of 1x times the tangent of 2x? You can't do that. You can only multiply them if they have the same angle inside, 1 and 1, 2 and 2, but you can't mix and match them if they don't agree, and that's really more for the third day. So here is the homework for tonight, homework number 60. You're going to go ahead and try these 7 problems. Again, pay attention to the directions, whether it's general solution or 0 to 2 pi. This lesson not only reviews these new techniques, but it also refreshes your memory for lesson 59. So thanks very much for tuning in, guys, and we will catch you next time.